So displacement reaction. In displacement reaction, an atom or ion present in a compound that replaced by the atom of ion of the another element. Right? For example, if I say this X is replacing the Y, X atom is replacing the atom's Y, right? Hello, Jama? Right.
Yeah.
So can I say that X is more reactive than Y? Right. So X has displaced Y from the compound YZ. This type of reaction is called as a displacement reaction. Right. So these displacement reactions have been classified into two types, depending upon whether metal or non-metal is involved in the displacement. I'll discuss this, what is meant by the metal or non-metal here. Right. A metal present in a compound gets displaced by the metal in uncombined form, provided it occupies a position higher in the activity series. It means the substance that is more reactive will displace the less reactive element. Right. More reactive will displace the less reactive element. In this reaction, you can see zinc is replacing iron. Here there is some misprinting here. It should be zinc sulfate here. Right. So I can say zinc is more reactive as compared to iron. That is why zinc is replacing iron here. Right. Here sodium is more reactive than magnesium. That is why magnesium is replacing the magnesium from its magnesium oxide. So the element that is more reactive will displace the less reactive element. Am I clear? So what is happening in this equation? You can see the oxidation number of the zinc is converting from zinc to 0 to +2 here, or magnesium or sodium is changing to +1 here. It means sodium is more reactive. It loses electrons so easily as compared to the magnesium, and magnesium gains the electron. Magnesium get reduced, zinc get oxidized. I can say this is a redox reaction. One substance is undergoing oxidation and other substance is undergoing reduction. Right, getting me?
Yeah.
So let us discuss this in its application in the metallurgical operations, right, where the less reactive element will be replaced by the more reactive element when we can get a pure substance. So there we will be using some reducing agent like this. I'll give an example for this one. That is, if I want to get chromium, then aluminum is more reactive than chromium. Aluminum displaces chromium from chromium oxide. Right? This type of reaction is called as a what do you call? Displacement reaction, right? And you can see that here aluminum is undergoing oxidation and chromium is undergoing reduction. Oxidation number of aluminum is increasing from 0 to +3. It means aluminum is undergoing oxidation and chromium is undergoing reduction, +3 to 0. By this way, we are getting the chromium metal, extraction of chromium from its oxide, and it is a displacement reaction, right? And now similarly, we have got the vanadium from its vanadium oxide by using calcium. So calcium is more reactive as compared to vanadium, and here again through its oxidation number I am showing that calcium is undergoing oxidation from 0 to +2 and vanadium is undergoing reduction from +5 to 0. Such type of reactions are called as a displacement reactions. Similarly, we can give one more example here. Titanium chloride is treated with magnesium, and magnesium is more reactive as compared to titanium. So basically what you're finding here is more reactive element displaces the less reactive element, right? And in the first two cases where you can see oxide is converting into the metal, I can say from the chromium oxide the oxygen is being removed. What is loss of oxygen called? What is loss of oxygen called? Reduction.
Yeah.
So I can say here aluminum is acting like a reducing agent. Here in the second case, calcium is acting like a reducing agent. In the third case, you can see the titanium oxidation number is decreasing, or I can say titanium is getting reduced in the presence of magnesium. So magnesium is a reducing agent, right? Similarly, I'm one more example here. Here the gold +1 state and gold 0 state, it means gold is getting reduced. Gold is getting reduced in the presence of zinc. So zinc is acting like a good reducing agent. Is this clear?
Right.
So the application of redox reaction is in the extraction of the metals. Now we discuss about the non-metal displacement. Are illustrated by hydrogen displacement reactions. A reactive metal like sodium, potassium, calcium displace hydrogen by reacting with water. So I'll discuss it with some example here, like this. So you can see the hydrogen is being replaced by the sodium here. The non-metal hydrogen is replaced by the sodium here. It's a displacement reaction. And again, I can say the sodium is more reactive as compared to hydrogen. So sodium is undergoing oxidation from 0 to +1, and hydrogen is undergoing reduction from +1 to 0. Am I clear?
Yes.
So in the second case, can I say that potassium is more active as compared to hydrogen? And that is why potassium is displacing hydrogen from the water. Can you tell me out of sodium and potassium, which is more reactive?
The sodium.
No, it is potassium, because you know that sodium and potassium are in the same group number 1 of the periodic table.
Right.
As you go down the group atomic size,
gets bigger.
Yeah. So tendency to lose electrons
is more,
and the reactivity will be more, right?
Okay.
Similarly, you can see calcium is displacing hydrogen from water, and it is a displacement reaction. Am I clear? All right. Now, less reactive metal like magnesium, iron displaces hydrogen on passing steam, not in presence like cold water, but in the presence of the steam, right? So in hot water, like here water is hot, and with the iron the water is in the gas state, here is the steam form, because here magnesium and iron are less reactive as compared to sodium or potassium or calcium. They react in cold condition also, but here magnesium and iron, which are comparatively less reactive, they react in the heated water or in passing the steam. Am I clear? So again, you can see the magnesium is displacing hydrogen, and here the removal of oxygen is called as reduction. So you can see the water is getting reduced to hydrogen, and iron itself is getting reduced by reacting by combining the oxygen here. I hope it's clear.
So the magnesium is the reducing agent because it's taking.
Magnesium is, of course, it is acting like a reducing agent. Yes. In
Okay.
the second case, iron is acting like a reducing agent.
Mhm.
Now, less reactive element like zinc react with HCl and displaces hydrogen and produce hydrogen gas. You can see removal of electronegative element is also called as a reduction. Last time I discussed about it.
Mhm.
So zinc 0 to plus 2, it means zinc is undergoing oxidation, and hydrogen plus 1 to 0 means reduction. It
Right.
means zinc acts like a reducing agent and HCl acts like an oxidizing agent for the zinc. Zinc is losing
Okay.
electron only in the presence of HCl. It
Mhm.
means HCl acts like a oxidizing agent, and zinc is giving electron to the H positive ion to become H2. It means zinc acts like a reducing agent, right?
Mhm.
Now, here in the second case, magnesium reacting with the sulfuric acid, you can see the hydrogen is replaced by the magnesium, and we get a magnesium sulfate and H2 gas.
Mhm.
Again, we can say magnesium is acting like a reducing agent, and H2SO4 is a good oxidizing agent. You can see the change in oxidation number. 0 2
Mhm.
plus 2, magnesium 0 2 plus 2, it means magnesium is getting oxidized.
Oxidized. Yeah.
It means sulfuric acid is a oxidizing agent,
Mhm.
and sulfur plus 6, sorry, hydrogen plus 1 to 0 on the product side. It means hydrogen is getting reduced in the presence of the magnesium. It means magnesium acts like a reducing agent.
Research.
Getting me, Jana?
Yeah.
Okay. Similarly, we can give one more example here. Iron reacting with HCl. So 0 2 plus 2, iron 0 2 plus 2 in the presence of HCl. You tell me now, what is iron? What is happening with iron? Oxidation or reduction? Oxidation or reduction? What is happening with it?
So the oxidation, like it's exchanging the electrons, right?
My question is very simple here. What is happening with iron? Whether it is undergoing oxidation or reduction?
Oh, so this is oxidization because
Oxidation.
it's,
Yeah, it's losing electron.
yeah.
So it is happening in the presence of HCl. So can I say that HCl is a oxidizing agent?
Mm-hmm.
And what is happening with the hydrogen from the reactant side plus 1 to 0?
It's being reduced
Reduced in the presence of
of the
iron.
iron
So iron is a
or reducing. I mean, yeah, reducing it.
reducing agent. So all these reactions are applied to evolve hydrogen gas in the lab,
Mm-hmm.
right? Now, fluorine is so highly reactive that non-metal displaces oxygen from water as follows. HF is formed and O2 is liberated here. So what is happening with the oxygen? Minus 2 to 0. Oxygen minus 2 to 0. What is happening with oxygen? Oxygen oxidation reduction.
The oxygen is being oxidized.
Oxidized in the presence of the fluorine. So
Mm-hmm.
I can say fluorine is a good oxidizing agent. Of
Mm-hmm.
fluorine like oxidizing agent here. Fluorine 0 to minus 1. What is happening to fluorine?
It's being reduced.
In the presence of
Oxygen.
water.
Yeah.
The water acts like a
Reducing it.
reducing agent, right? Okay.
Mm-hmm.
Now we can apply this. The main application of these reactions is the hydrogen displacement reactions. The reactivity of the halogens, fluorine is more reactive as compared to chlorine, chlorine is more active as compared to bromine, and bromine is more active as compared to iodine. So more reactive halogen displaces the less reactive halogen from its salt, right? For example, chlorine displaces both the bromine and iodine from its salt solutions, but chlorine cannot displace the HF or NaF because fluorine is more reactive as compared to chlorine, right? I'll now explain it with some examples here. Here, you can see the chlorine is more reactive compared to iodine. Here, there is a misprinting here. It should be I2 molecule here. Br2, in place of Br2, it should be I2.
Okay.
So, chlorine is displacing iodine because chlorine is more reactive as compared to iodine. Right? In the second case here, the chlorine is displacing iodine. That's the correct equation now. I'm giving the correct equation here. It is because the chlorine is more reactive as compared to iodine. But bromine cannot displace chlorine, but does displace iodine from its salt solution. Let us see this example here. Bromine, of course, bromine is more reactive as compared to iodine, right? So this reaction is possible. Am I clear? Right. Now, I'm talking about the disproportionation reaction. What is disproportionation reaction? Last time I told you, in which same substance undergoes oxidation as well as reduction in the same reaction.
Okay.
For example, if I say I have this reaction, wait, please. Yes. What is the oxidation number of oxygen in the reactant side? I have shown here it is -1. And after the reaction, after decomposition of H2O2, hydrogen peroxide, it is giving -2 and 0. -1 to -2 is reduction, and -1 to 0 is oxidation. It means here oxygen is undergoing oxidation as well as reduction. Such substances are called as a disproportionation reaction. Am I clear?
Right.
Now, take up this example here. Phosphorus, 0 here on the reactant side, and -3 on the product side, and +1 here on the another compound. So 0 to -3 is reduction, and 0 to +1 is oxidation. It means phosphorus is undergoing reduction and oxidation all together in the same reaction. Such type of reactions are called as a disproportionation reaction. Am I clear? Now, take up this case now. Chlorine, 0 here, +1 here, -1 here. 0 to +1 is oxidation, and 0 to -1 is reduction. So, chlorine is undergoing disproportionation reaction. In this case, manganese, 0 to +3 to +7. Is it 0 here? Calculate here. Check. MnO4 2 -. Calculate for manganese here. I think it is +6. Yeah. +6 on the reactant side, +6 to +3 reduction, and +6 to +7 is oxidation. Am I clear?
Yeah.
Okay. Now, all these reactions are disproportionation reaction. In case of NO2, in case of copper or 1 positive ion, all these reactions where the oxidation number increases as well as decreases, that reaction is called as a disproportionation reactions. Clear? No. I'm starting with the another topic of this chapter. It is known as chemical cell or also called as a galvanic cell. Do you know something about this electrochemical cell or galvanic cell?
No, I don't think so.
Okay. Have you ever seen the battery cells?
Mm-hmm.
They convert the chemical energy into electrical energy.
Mm-hmm.
That device, that cell, which converts the chemical energy into electrical energy, is called the electrochemical cell.
Mm-hmm.
Now, see here. What we have done, we have set up a cell here. In this beaker, we have a copper sulfate and silver rod here. Here I have copper sulfate and zinc rod here. And I connect it to the chlorine. Just a minute, wait, I will discuss it with different example here. No, just a second. I'll explain the electrochemical cell separately. See, here I'm showing here one example here. Here I have a copper sulfate solution, 1 molar copper sulfate solution, right?
Mm-hmm.
And I'm dipping here a zinc rod. After some time, what do we observe? Certain observation I'll tell you. Number 1, zinc rod is eaten away. Right?
Mm-hmm.
Zinc rod is eaten away. Means it happens like this. Here, the zinc rod gets dissolved. That's what I mean by the eaten away. Second is blue color of copper sulfate fades away. Right?
Mm-hmm.
Number 3, copper metal deposit at the bottom. Right?
Mm-hmm.
To explain these observations, a theory was proposed here. That theory was electrochemical theory. Now I'll discuss about an electrochemical theory. What is this electrochemical theory? This theory states that zinc undergoes oxidation. It means from solid it is converting into the aqueous ion.
Mm-hmm.
And in the solution we have copper ions. They gain electron and become copper. It means from the aqueous solution they are getting converting into solid. So electrons are lost by the zinc and gained by the copper ions.
Mm-hmm.
What is loss of electron called? What is loss of electron?
Oxidation.
So I can say this is a oxidation half reaction.
Mm-hmm.
And the gain of electron is called as a
Reduction half.
So I can say it's a reduction half reaction. Are you getting me?
Uh-huh.
So cancel out the electrons here and we get here zinc plus copper ions to give copper and zinc ions. Solid, aqueous, solid, aqueous. Such type of reactions in which reduction and oxidation occur simultaneously is called as a redox reaction.
Mm-hmm.
Getting me? So in this case, what has happened here is, what has happened to sulfate ion now? Can you tell me? Sulfate ions were initially bonded with the copper ions, and now it is connected with the zinc ions. But sulfate ions do not undergo any change in oxidation number. So sulfate ions are not undergoing any change in the oxidation number. That ion is called as spectator ions. That ion is called as spectator ions. Right? They are just spectators. Loss and gain is by the zinc and copper only, and spectator ions are initially bonded with the copper ions, and now they are bonded with the zinc ions. Right. Now in this theory, can you see that electrons are moving from zinc to copper? Can you tell me what is the flow of charge called?
Is it like
What is flow of charge called?
Electromagnetic ring?
No,
or electrochemical.
That is simply called the current.
Oh, right.
It means electricity is generated by this reaction. When reaction is going on, the electrons are lost by the zinc ions and gained by the copper ions. It means there is a flow of charge from zinc to copper, and such thing is called as a current. It means the device we have generated now, that is called as a electrochemical cell, which converts the chemical energy into electrical energy. Am I clear? Right. Now let us do one experiment here. It means if you put up here two wires here and connect it with a bulb, the bulb should glow or not?
Right.
It should glow, right? But actually it does not glow at all.
Is it just not enough?
No. It means we are going theoretically correct. Scientifically we are absolutely correct. But there may be some technical error here, due to which the bulb is not glowing. Can you tell me what is that error? Theoretically we are okay, that electrons are lost by the zinc and gained by the copper, and electrons, while they're moving.
So like in reality, like they might be going other places, not like to the copper.
Actually, see the technical part of it. But technically, what should be the under what condition the current will be flowing? Number one, circuit must be complete.
Closed circuit.
Yeah. Here circuit is not complete. Right. From one end, electron should go inside. From the other side, electron should come out, and it is not happening here. The circuit is not complete. Number one problem here. Right. And second is, between the two ends of the conductor there should be potential difference. In physics you might have studied about the potential difference, voltage difference, right? And there is no any device, there is no any phenomena which is creating the potential difference between the two ends of the conductor. Right. So that's what is happening here. So I told you two problems due to which the reaction is not going on. Number one, circuit is not complete, and number two,
because of the voltage difference.
Yeah, that there should be some potential difference, right? So that is not there. So to solve this problem, what we have done is we have converted this cell into two beakers. Now we say redox reaction will take place now in two beakers. In the first beaker we have taken here 1 molar copper sulfate solution, and I had dipped here the copper rod only. It means nothing will happen now. In the previous case, what we did was, in the copper sulfate solution we dipped the zinc rod. Reaction was taking place. But now what I have done is, in the copper sulfate solution I had dipped the copper rod. Reaction will not take place. And here I have a zinc sulfate solution. of 1 molar, and I had dipped here the zinc rod. Now nothing will happen. Now when I connect here, right, here I have a voltage, some voltmeter here. There are certain observations that I will not tell you. What is our observation? Number one, again, I can say zinc rod is eaten away. Number two, copper metal deposit on copper rod. Number three, blue color of copper sulfate fades away. Number four, voltmeters show deflection towards copper. And number five, very important, cell stops working after some time. It means our chemical is not complete, is not completely consumed, but the reaction has stopped. Now I'll be discussing the reason for all this, why it is happening here. Again, a theory was given that is known as electrochemical theory. I'll be discussing about that electrochemical theory now, right? It was proposed like this, that zinc that is solid undergoes oxidation, and these electrons start traveling from zinc to copper. Okay, and zinc ions comes into the solution as a zinc ion. Is that clear?
So yeah, so they get transferred.
Yes. So zinc comes into the solution as zinc ions. And now when these electrons come on this copper rod, from here the copper ions get attracted to gain electron. As they're coming closer to the gate to gain electron, what will happen here, that copper ions which are in the aqueous solution gain electron and become copper rod and get deposited in the copper rod. Am I clear? So in this case, what is happening? Zinc is a source of electron. Zinc is a source of electron. I repeat, zinc is a source of electron and giving electron, and it means it is negatively charged. And oxidation is going on at anode, so zinc acts like an anode. Now electron move towards the copper, and here the gain is going on, and it is called as a cathode, and it is positively charged. That is why electrons are attracted towards it. Right? It means electrons are flowing from zinc to copper. So electrons are moving through the wire. Zinc is getting converted into zinc ions. So I can say zinc rod is eaten away. This concept is not clear. This observation that zinc rod is eaten away because zinc is undergoing oxidation, and when the copper ions get deposited on the copper like this, because they are undergoing reduction here, so copper ions get deposited on the copper, and the blue color will fade because the concentration of the copper ions will decrease. Right. So this observation is also okay now. I am discussing all these observations with a theory, and electrons are moving from zinc to copper, and our all devices show deflection opposite to the flow of electron. From zinc to copper, we have an electronic current. And from copper to zinc, we have conventional current. Right? From zinc to copper, we have electronic current, and from copper to zinc, we have conventional current. Am I clear?
Yeah.
And that is why I can now say that voltmeters show deflection towards copper. Sorry, towards zinc. I should write here zinc. Right, opposite to the flow of electron.
Right.
Right. And now the last point is very, very important here. Why cell stops working after some time? Right, our chemical is not complete, is not completely consumed. Our zinc rod is not completely oxidized. All the copper ions have not got deposited in the copper. But still the reaction stops. I will discuss why so. Right. Reason here is, initially zinc ion concentration and sulfate ion concentration, they were equal in number in the ratio of 1:1, right? Initially, when we didn't start the process.
Right.
But after the process, what happened? The zinc ions concentration is increasing, but sulfate ion remains same. You can see the zinc ions are getting added to the solution here.
Yeah.
Right. So I can see the positive ion concentration will increase here, and it will become positively charged. The solution will become positively charged.
Right.
And here, in the other case, other beaker, initially the copper ions and sulfate ions were equal in number, but with the passage of time, the copper ions getting deposited, and the copper ions become less as compared to sulfate ion. And due to that, what will happen? This solution will become negatively charged because of excess of sulfate ions. Now what will happen then? The positive field of this solution will not allow the electrons to move away from it, because electrons are negatively charged and the solution is getting positively charged. So this positive field will not allow the electrons to move away from it. And if by chance the electron goes to the copper, the negative field of the solution will repel the incoming electrons. And thus the flow of electron is not allowed anymore. From one side, electrons are not allowed to go away, and from the other side, electrons are not come in. Are not allowed to come in. It means the flow of electron will stop now. It means voltmeter will show 0 reading and cell will stop working. Will stop working. So that was my observation, how we discussed it, that why it is happening. But now again a question arises here, that I want that the cell should continue working until the complete chemical is consumed. I want this, right? I want that cell should continue working until there is a chemical, until there is a copper rod, until there is a zinc rod, until there is a copper solution, right? When all the chemical is completely consumed, means zinc is completely dissolved and copper ions are completely getting absorbed, then cell stops, it's okay. But the problem is my zinc rod is still left and copper ions are still more left in the copper sulfate solution, and cell is stopping. I don't want that. I want the cell should continue working. And to make it possible, what we are introducing is a salt bridge.
Okay.
This bridge will now help you to continue the cell. Right. Now, what is this salt bridge and how it will work? And now I'm discussing that. Right.
Okay.
Salt bridge is basically a U-shaped tube, and I'll say inverted U-shaped tube. Okay. I will use it in the inverted form, and here I have a cotton plug. This is a cotton plug. And here I have potassium chloride or potassium nitrate or ammonium nitrate. Any one of these I'll fill here. In a special gel, we call it the agar-agar gel. And this salt bridge is now inserted into this cell. This cell. Getting me? Now, how will I introduce this? Let us see. This is introduced like this. Okay. I'll make it fresh. Here I have copper sulfate solution, right? With copper rod in it. Here I have a zinc rod dipped in the zinc sulfate solution. And connecting it with key voltmeter. And here is the salt bridge. Right? Here I have electrons are moving from here to here, right? Deflection towards the zinc, and inside it, let it be, I have filled here the potassium ions and the chloride ions. Now, in the process with the cell is going on, which ion concentration is increasing in the zinc sulfate solution?
This zinc ion.
There is extra zinc ions, and here we have an excess of the sulfate ions, right? And here the potassium chloride is here, so the chloride ion will come out to combine the zinc ions.
Right.
And it will become neutral now. And from here the potassium ions will come out to combine the potassium with the sulfate ion. Are you getting me? So the solution become neutral now. And the cell will keep on working until whole of the copper ions are getting deposited and whole of the zinc is oxidized. Because the cause was the accumulation of the charge that was stopping the process. Right? And now by this way we are not allowing any ion accumulation in any beaker. We do not allow any ion to get accumulated in any beaker, and that is why the cell will continue working now. Am I clear?
Yeah.
Right. So now my question arises here: which metal is undergoing oxidation?
The zinc, right?
Zinc is undergoing oxidation, and copper is undergoing
reduction.
Right? Okay. Okay, now can I do this one?
Which of the following compounds has a list? oxide is is it C?
Yeah. How much it is?
Should be 0
+1.
+1. Oh, Fe is +1.
Yeah, because O is 2 minus 2, right? Okay. Yeah.
In the reaction between zinc and iodine, the same kind. What is the reduction of copper in the case?
Let us see.
From your example that you were talking about, right?
Yeah, zinc plus iodine,
Yeah.
right? Zinc iodide is formed. Zn-ito, right? Zinc 0 to +2 and iodine 0 to -1, right? So what is being oxidized? Zinc 0 to +2, right? So it is undergoing oxidation, right? So it's the oxidation of the zinc.
Yeah, it
Yeah,
says
all the options,
like,
all these options are wrong.
yeah.
Right.
I was like, okay.
Anyways.